We have always been told that the speed of light is the ultimate limit on how fast anything can travel through the universe. But what if the true barrier has nothing to do with energy at all? What if the real obstacle is noise? Not the noise of sound waves rattling through air, but a deeper, stranger kind of noise woven into the fabric of empty space itself. Our dreams of warp drives and faster-than-light voyages are running into a wall that few people, outside of theoretical physics, ever hear about. And it has almost nothing to do with how many rockets we build or how much energy we can generate. It has to do with something happening at scales so small that a single atom looks like a mountain range by comparison. That barrier is called subatomic decoherence, and it may be the quiet, invisible force that keeps humanity tethered to sub-light speeds for far longer than science fiction ever promised us. In the year 2024, a wave of new simulations reignited hope among physicists and space enthusiasts alike. Researchers had been refining old ideas about warp bubbles, regions of space where the geometry itself is bent, so that the space in front of a ship contracts while the space behind it expands. The ship does not move through space in the traditional sense. Instead, space moves around the ship, carrying it along like a raft riding a wave, without technically breaking the light speed limit for objects moving through space. These 2024 simulations suggested that some of the outlandish energy requirements once thought necessary for such a bubble might be reduced dramatically, using clever configurations of exotic matter and carefully shaped space-time curvature. For a moment, it felt as though the door to the stars had cracked open just a little wider. But a warp bubble, if it could ever be built, would not simply be a matter of pouring in enough energy and watching space fold like origami. It requires something far more delicate, a perfectly tuned local region of space-time, sculpted with an almost impossible level of precision. Even a tiny deviation in the curvature, even a flicker of instability in the field holding that bubble together, could cause the entire structure to collapse before it ever accomplished anything close to faster than light travel. And this is where the conversation shifts, because it turns out that energy, as staggering as the numbers can be, might not be the primary obstacle after all. The primary obstacle might be maintaining quantum stability long enough for the bubble to do what it is meant to do. Quantum stability is a phrase that sounds abstract until you realize how universally fragile it is. Every quantum system, whether it is a single electron or a colossal theoretical structure like a warp bubble, exists in a delicate balance. The moment that balance is disturbed by outside influence, the system tends to fall out of its precise quantum state and settle into something far more ordinary and far less useful. This disturbance has a name in physics, and decoherence, as we are about to see, might be the single greatest engineering challenge standing between humanity and the stars, dwarfing even our wildest energy requirements. If you were to imagine the vacuum of space, you would probably picture something close to nothing at all, a silent, motionless void stretching endlessly between stars. That image, comforting as it is, turns out to be almost entirely wrong. Modern quantum field theory paints a very different picture, one where empty space is never truly empty. Instead, it behaves more like a boiling sea, constantly rippling with what physicists call virtual particles, pairs of particles and antiparticles that spontaneously appear and disappear in tiny fractions of a second, borrowing energy from the uncertainty inherent in quantum mechanics before annihilating each other and vanishing again. This is not speculation drawn from the fringes of physics. This behavior emerges directly from the mathematics of quantum electrodynamics, one of the most rigorously tested theories in all of science, confirmed to extraordinary precision through decades of experiments. The theoretical foundation for these virtual particles traces back to the energy time uncertainty principle, one of several forms of Heisenberg's famous uncertainty relation, which states that a quantum system can briefly borrow energy from the vacuum, provided that energy is repaid quickly enough, with the maximum allowable duration growing shorter as the borrowed energy grows larger. This is not a loophole or a violation of energy conservation, but a precise mathematical consequence of the wave-like nature of quantum fields, confirmed indirectly through phenomena like the Casimir effect and directly through the measurable influence virtual particles have on the magnetic properties of the electron. One of the most precisely tested predictions in the entire history of physics. It is worth appreciating just how well established this piece of the picture is, because it means the restless, fluctuating vacuum described throughout this documentary is not speculative window dressing borrowed loosely from physics to make a compelling narrative. It is one of the most rigorously confirmed features of the universe we inhabit. There is also an important and often underappreciated source of decoherence that has nothing to do with the exotic Planck scale physics discussed so far, and everything to do with the discovery made accidentally in 1965, the cosmic microwave background. The faint, pervasive thermal radiation left over from the early universe, cooled over billions of years of cosmic expansion to a temperature only a few degrees above absolute zero. Even this famously cold relic of the Big Bang represents a real, measurable source of thermal photons filling every corner of space, and any warp bubble attempting to form anywhere in the observable universe would need to contend with this ever-present bath of background radiation as an additional, unavoidable source of environmental interaction, layered on top of the more exotic vacuum fluctuations occurring at the Planck scale. In deep intergalactic space, far from the thermal noise of stars and planets, this cosmic microwave background represents close to the coldest, quietest environment the universe has to offer, and even there, the noise floor never quite reaches zero at the smallest conceivable scale, a distance so tiny it is almost meaningless to try to visualize it. Something called the Planck scale. These fluctuations become almost violent. Space and time themselves are thought to lose their smooth, continuous character and instead churn with a kind of quantum foam, a term coined by the physicist John Wheeler decades ago to describe how spacetime might behave when examined at its most fundamental level. This foam is not something we can observe directly with any instrument built so far, since it exists far below the resolution of even our most powerful particle accelerators, but its consequences ripple upward, subtly influencing everything built from quantum fields, which is to say, everything in the universe. This is the environment that any warp bubble would have to exist within. Not a peaceful vacuum, but a restless, fluctuating quantum background that never stops interacting with whatever structure tries to maintain a stable, coherent state within it. Environmental interaction is the technical term physicists use to describe how a quantum system becomes entangled with its and every single entanglement event chips away at the delicate coherence that the system needs to preserve. Imagine trying to balance a perfectly still glass of water on a table that never stops vibrating. Even the smallest, most imperceptible vibration eventually causes ripples, and given enough time, those ripples spill the water entirely. The vacuum of space is that vibrating table, and a warp bubble is that glass of water. Except the vibrations here are not mechanical, they are quantum mechanical, occurring at scales far beyond anything we can shield against using conventional materials. Here lies one of the most counterintuitive discoveries to emerge from decades of quantum research. These microscopic fluctuations are not just a minor background hum easily ignored. They appear to be the dominant source of early-stage decoherence for any large-scale coherent field. including the kind of field a warp bubble would require. Physicists studying quantum computing have run into an almost identical problem, though on a vastly smaller and more manageable scale, and their hard-won lessons offer a sobering preview of what any future warp engineers would face. Keeping even a handful of qubits coherent for a fraction of a second requires isolating them inside near absolute zero refrigeration systems, shielding them from electromagnetic interference, and constantly correcting for errors introduced by the surrounding environment. Now imagine trying to do the same thing, not for a handful of subatomic particles, but for an entire localized region of spacetime large enough to carry a spacecraft. The deeper we look into the mechanics of a warp bubble, the more it starts to resemble not a feat of brute engineering, but an act of impossibly precise quantum choreography. A warp bubble, according to the mathematics developed by physicists exploring these exotic solutions to Einstein's field equations, requires what is known as a pure quantum state to maintain its unusual geometry. A pure state is, in simple terms, a quantum system that has not yet become entangled with its environment, one that still holds onto its full coherence and its full potential for the strange, non-classical behavior that quantum mechanics allows. The moment a system becomes entangled with the outside world, even slightly, it transitions toward what is called a mixed state, losing the very properties that made it useful for exotic physics in the first place. For a warp bubble, that pure state is not a luxury. It is the entire foundation of the concept. The exotic geometry required to bend spacetime in the specific way needed to create the warp effect depends on maintaining coherence across the entire structure of the field simultaneously. If even a small portion of that field becomes entangled with the surrounding vacuum, with its restless virtual particles and Planck scale fluctuations, the coherence begins to unravel. And once it starts unraveling, it does not do so gently. Much like a row of dominoes, the loss of coherence in one region tends to cascade outward, destabilizing the rest of the structure in a rapid, self-reinforcing collapse. It is a strange and almost poetic detail that the cosmic microwave background, so often celebrated as one of the great triumphs of observational cosmology, confirming the Big Bang model with extraordinary precision and offering cosmologists a snapshot of the infant universe only a few 100,000 years after its birth, doubles here as a quiet obstacle to one of humanity's oldest dreams. The same relic radiation that helped confirm how the universe began may also help explain why some journeys across it will always remain difficult. A small but telling example of how deeply interconnected different corners of physics really are, even when they appear, on the surface, to belong to entirely separate conversations, and a reminder that in a universe this intricately woven together, even the coldest silence still carries a whisper of noise. This is where an important and often overlooked idea comes into focus. Before you can even begin to worry about whether a warp bubble might successfully propagate faster than light, you first have to answer a much more basic question. Can the bubble survive its own formation? According to the physics of decoherence, the answer appears to be extraordinarily difficult to satisfy. The wave function describing the bubble's exotic quantum state would need to remain coherent, not for a hypothetical future moment of propagation, but from the very first instant of its creation, through every stage of stabilization, all while surrounded by a vacuum that is actively working at every scale. To destroy that coherence, think of it like trying to light a match in the middle of a hurricane. It does not matter how skillfully you strike the match or how much fuel you have prepared, because the surrounding environment is simply too chaotic to allow the flame to take hold. The vacuum of space, far from being a calm backdrop for our ambitions, behaves more like that hurricane, constantly buffeting any attempt at coherent, large-scale quantum behavior with a storm of interactions, happening on timescales far shorter than we can currently measure or control. Scientists studying the collapse of these theoretical warp fields describe the process using the language of wave function collapse, a concept originally developed to explain much smaller quantum systems, like the famous thought experiment involving a particle that exists in a superposition of states until it is measured or otherwise interacts with its environment. When that interaction occurs, the particle's wave function collapses into a single definite state, and all the strange quantum possibilities it once held simply vanish. A warp bubble, if we take the mathematics seriously, behaves the same way, except now we are talking about a wave function representing not a single particle, but an entire structured region of curved spacetime. This collapse would happen before the bubble ever reached what physicists refer to as a propagation threshold, the point at which its geometry becomes stable enough to actually begin moving faster than the normal speed of light relative to distant observers. In other words, the bubble might dissolve back into ordinary uncurved spacetime before it ever accomplishes the very task it was built for. All of that theoretical exotic matter, all of that carefully calculated negative energy density, would simply dissipate into background radiation and heat, with no faster-than-light journey to show for it. This subatomic friction, as some researchers have taken to calling it, functions almost like a cosmic brake system built directly into the laws of physics. It is not a brake in the traditional sense of something that resists motion through applied force. It is a brake that prevents the very possibility of motion from ever fully forming, by dissolving the coherent structure required before that structure can detach from ordinary spacetime and begin its journey. And unlike energy requirements, which at least in principle could be addressed through advances in propulsion technology or exotic matter production, this friction seems to be baked into the fundamental behavior of quantum fields interacting with a fluctuating vacuum, making it a far more stubborn problem to solve. To understand why this barrier is so difficult to overcome, it helps to look at a field of research where scientists are already fighting this exact battle, just on a scale small enough to be manageable with current technology: quantum computing. Modern quantum computers work by manipulating qubits, the quantum equivalent of the ones and zeros used in classical computing. Except a qubit can exist in a superposition of both states simultaneously, at least until it is measured. This superposition is what gives quantum computers their extraordinary potential processing power for certain types of problems. But that same superposition is astonishingly fragile, and maintaining it is one of the greatest engineering challenges in modern physics. Companies and research institutions building quantum processors have discovered, often the hard way, that qubits lose their coherence extremely quickly when exposed to almost any environmental disturbance. Stray electromagnetic fields, tiny vibrations, even background thermal radiation from the surrounding materials can be enough to collapse a qubit out of its useful quantum state. This is why quantum computers are typically housed in elaborate cooling systems, chilled to temperatures colder than the depths of interstellar space, often just a fraction of a degree above absolute zero, in an attempt to minimize the thermal noise that would otherwise destroy coherence in a matter of microseconds. Even with these extraordinary precautions, coherence times 4 qubits remain frustratingly short, often measured in fractions of a second. And error correction has become an entire subfield of quantum computing, research dedicated to compensating for the inevitable noise that creeps in despite every effort at isolation. If maintaining coherence in a system of a few dozen or a few hundred qubits requires this much engineering effort, it raises a sobering question about what it would take to maintain coherence across a macroscopic region of spacetime large enough to transport a spacecraft and its crew. The relationship between system size and decoherence rate is not linear, unfortunately. As physicists have discovered through both theory and experiment, decoherence rates tend to increase disproportionately as the number of interacting particles or the complexity of the system grows. This is sometimes described as an exponential relationship, where each additional degree of freedom in a quantum system introduces new pathways through which the environment can extract information and destroy coherence. A single isolated particle might remain coherent for a relatively long time. A system of a few particles decoheres much faster, and a system on the scale required to warp spacetime around an entire vehicle would involve so many interacting degrees of freedom that current theoretical models suggest coherence could be lost almost instantaneously, long before any macroscopic effect could take hold. This is the heart of what some physicists have started referring to as the noise floor, a fundamental physical boundary imposed not by any particular technological limitation, but by the underlying statistical behavior of quantum systems interacting with their environment. Just as a radio signal can only be detected if it rises above the background static of thermal and electromagnetic noise, a coherent warp field would need to somehow rise above the quantum noise floor of the vacuum itself, a noise floor that appears to scale upward rapidly as the size and complexity of the field increases. Rather than a wall we might eventually punch through with enough raw power, the noise floor behaves more like quicksand, becoming harder to escape the more we struggle against it with sheer energy alone. If you find yourself wondering whether this means faster than light travel is permanently impossible, you are asking exactly the right question, and it is worth pausing here to really sit with the idea, because the answer scientists are converging on is more nuanced than a simple yes or no, and it changes how we should think about the entire future of interstellar ambition. If a question like that keeps you curious the way it keeps physicists curious, it is worth sitting with a moment longer before we keep going, because the deeper we go here, the stranger and more surprising the picture becomes. To appreciate how we arrived at this understanding of decoherence, it helps to step back into the history of quantum mechanics itself, a history filled with debate, confusion, and eventually remarkable clarity. When quantum theory was first developed in the 1920s by physicists including Erwin Schrödinger, Werner Heisenberg, and Niels Bohr, one of the strangest puzzles it introduced was the question of measurement. Why does a quantum system, capable of existing in multiple states simultaneously according to the mathematics, always appear to settle into a single definite state whenever we actually observe it? This became known as the measurement problem, and for decades it remained one of the most philosophically troubling aspects of an otherwise extraordinarily successful theory. It was not until the 1970s that a German physicist named Heinz Dieter Z proposed a compelling answer, one that did not require any mysterious role for a conscious observer, a notion that had crept into some interpretations of quantum mechanics and troubled many physicists who preferred explanations rooted purely in physical interactions. Z suggested that the appearance of collapse was not really collapse at all in the traditional sense, but rather the natural consequence of a quantum system becoming entangled with a much larger environment, an environment so complex that it becomes effectively impossible to track or reverse the resulting correlations. This idea, later refined and popularized by physicists including Wojciech Zurek, became known as decoherence theory, and it has since become one of the most important frameworks for understanding how the strange quantum world gives rise to the familiar classical world we experience every day. Decoherence theory does not claim that superposition disappears entirely. Instead, it explains that the information describing the superposition spreads out, into the surrounding environment so thoroughly and so quickly that it becomes practically, if not fundamentally, irretrievable. From our limited perspective, as observers embedded within that same environment, the system simply appears to have collapsed into one outcome. This distinction matters enormously for our discussion of warp bubbles, because it tells us that the problem is not some mysterious act of cosmic observation reaching in from outside the universe to destroy our exotic space-time structures. The problem is baked into the ordinary, well-understood physics of how quantum systems interact with complex environments. Environments that in the case of a warp bubble would include the entire fluctuating vacuum of space itself. This brings us to a name that anyone interested in warp, Dr. Physics, eventually encounters: Miguel Alcubierre, the Mexican theoretical physicist who, in 1994, published a solution to Einstein's field equations describing exactly the kind of space-time warping we have been discussing. The Alcubierre metric, as it became known, showed mathematically that it was possible, at least within the framework of general relativity, to create a bubble of flat space-time that could move faster than light relative to distant observers, without violating relativity's prohibition against objects moving faster than light through local space-time. The trick, as Alcubierre demonstrated, lay in manipulating the space itself rather than trying to push an object through it. For years, the Alcubierre metric captured public imagination while remaining firmly in the realm of theoretical curiosity, largely because the energy requirements calculated from the original formulation were almost incomprehensibly large, requiring more negative energy than exists in the observable universe, according to some early estimates. Subsequent research throughout the 2000s and 2010s gradually chipped away at these energy requirements, with physicists finding clever, mathematical adjustments to the bubble's shape and thickness that reduced the necessary energy by many orders of magnitude. This is part of what made the 2024 simulations so exciting to those following the field closely. They represented the latest step in a decades-long process of making the warp drive concept seem progressively less impossible from an energy standpoint. But throughout this entire evolution, from Alcubierre's original 1994 paper through the refinements that followed, the question of quantum coherence received comparatively little attention. Most of the research focused on classical general relativity, treating space-time and the exotic matter required to warp it as smooth, continuous fields, rather than grappling with the underlying quantum nature of those fields. It is only in more recent years, as physicists have begun taking quantum field theory more seriously in the context of exotic space-time geometries, that the decoherence problem has moved from an afterthought to what many now consider the central unsolved challenge. There is a useful analogy that helps clarify why energy and coherence represent two entirely separate obstacles rather than to aspects of the same problem. Imagine trying to build an enormous, perfectly smooth glass sculpture in the middle of an earthquake zone. Having enough glass, enough furnace heat, and enough skilled craftsmanship to shape the sculpture addresses the energy and material side of the challenge. But no matter how much glass or heat you have available, the ground shaking beneath your feet will shatter the sculpture before it can ever be completed, unless you find some way to stabilize the environment itself. Reducing the energy requirement for a warp bubble is like figuring out how to make the sculpture with less glass. Solving decoherence is like figuring out how to stop the earthquake. Both are necessary, but they require entirely different kinds of solutions, drawn from entirely different branches of physics. This distinction has led some researchers to argue that the coherence problem may ultimately prove more difficult than the energy problem, precisely because it touches on such fundamental aspects of quantum mechanics, rather than simply requiring more advanced engineering or more exotic materials. Energy, after all, is something we have made extraordinary progress in generating, storing, and manipulating over the past 2 centuries. From the first steam engines to modern nuclear reactors to theoretical concepts like fusion, power, and matter, antimatter, annihilation. Coherence, on the other hand, seems to degrade according to principles that are woven directly into the mathematical structure of quantum theory itself. Principles that do not obviously bend to increased engineering effort in the same straightforward way that energy production does. Consider the sheer scale of the challenge involved in shielding a macroscopic warp field from environmental on Earth. Physicists attempting to preserve quantum coherence in laboratory experiments go to extraordinary lengths, using vacuum chambers, magnetic shielding, vibration isolation systems, and cryogenic cooling to protect delicate quantum states from the ordinary noise of our everyday environment. Yet even these heroic efforts typically only extend coherence times to fractions of a second for relatively simple systems involving small numbers of particles. A warp bubble would not exist within a laboratory vacuum chamber shielded from Earth's environment. It would exist within the vacuum of space itself, a vacuum that, as we explored earlier, is anything but empty, constantly alive with quantum fluctuations occurring at every scale down to the Planck length dot. This raises an uncomfortable possibility that no amount of conventional shielding could ever fully protect a warp field from its own environment, because the source of the interference is not some external contaminant that could be filtered out, but an intrinsic property of spacetime itself. You cannot shield a system from the vacuum by moving it somewhere else, because the vacuum is everywhere. This is fundamentally different from shielding a laboratory experiment from stray electromagnetic fields or vibrations, which are localized, identifiable sources of interference that can, in principle, be reduced or eliminated with sufficiently clever engineering. The quantum fluctuations of the vacuum represent something closer to an inescapable background condition of the universe itself. Interestingly, this connection between gravity and quantum decoherence is not entirely speculative territory, invented for the purposes of explaining warp drive failures. It touches on one of the most actively debated questions in theoretical physics, whether gravity itself might play a direct role in causing quantum systems to decohere, independent of any other environmental interaction. The physicist and mathematician Roger Penrose proposed an idea along these lines, suggesting that when a quantum system exists in a superposition involving different mass distributions, the resulting superposition of spacetime curvatures becomes inherently unstable, and the system spontaneously collapses into a single state after a timescale that depends on the mass involved and the degree of curvature difference. Penrose's proposal, sometimes discussed alongside a related idea developed independently by the physicist Laios Dios, remains unconfirmed experimentally, and it is important to be clear that it represents a hypothesis rather than an established theory. But it has inspired genuine experimental efforts to test whether gravity-induced decoherence is real, using extraordinarily sensitive optomechanical systems, tiny mirrors or crystals cooled to near their quantum ground state and placed into superposition to see whether they decohere faster than standard. Environmental noise alone would predict. If experiments eventually confirm some version of gravitationally induced decoherence, it would add an entirely new layer to the challenge facing warp bubble stability, because it would suggest that the very curvature a warp bubble depends on for its ergodic geometry might itself actively work against the coherence needed to sustain that geometry, creating a kind of built-in contradiction at the heart of the concept, even without invoking these more speculative gravitational decoherence theories. We can find sobering parallels in phenomena we already understand with much greater confidence. such as Hawking radiation near black hole event horizons. Stephen Hawking demonstrated in the 1970s that black holes are not perfectly black after all, but instead emit a faint thermal radiation caused by quantum effects occurring near the event horizon, where the extreme curvature of spacetime interacts with the quantum vacuum in ways that create real, detectable particles from what began as virtual fluctuations. This phenomenon illustrates something profound, that regions of extreme spacetime curvature do not simply coexist peacefully with quantum fields. They actively interact with and transform them, often in ways that dissipate energy and information outward into the surrounding universe. A warp bubble, by its very design, requires exactly this kind of extreme, localized spacetime curvature, the sharp transition zone between the flat region inside the bubble and the curved region required to propel it. If curvature near a black hole horizon is enough to spontaneously generate particles and radiate energy away, it raises a reasonable question about what similarly extreme curvature at the boundary of a warp bubble might do to the coherence of the quantum fields responsible for maintaining that boundary in the first place. This is an area of active theoretical exploration rather than settled science, but it reinforces a consistent pattern emerging across multiple, independent lines of physics research. Wherever extreme spacetime curvature meets quantum fields, the interaction tends to work against stability rather than preserving it. Meanwhile, back on Earth, experimentalists continue, pushing the boundaries of how large and how massive an object can be while still maintaining measurable quantum coherence, testing the practical limits of the decoherence problem in real laboratory conditions. Researchers have successfully placed increasingly large molecules, and in some experiments, tiny mechanical resonators containing trillions of atoms, into quantum superposition states, though only for extraordinarily brief periods, and only under painstakingly controlled conditions involving temperatures colder than deep space and isolation from virtually every conceivable source of environmental noise. These experiments, while astonishing achievements in their own right, also serve as humbling reminders of just how difficult it becomes to maintain coherence as systems grow larger, more massive, and more complex. Exactly the direction any real warp bubble would need to push toward on a scale vastly beyond anything currently achievable. Given everything we have explored so far, it might seem as though the story ends in defeat, with decoherence standing as an immovable wall between humanity and the stars. But physics rarely offers such simple, final verdicts, and the story of how researchers are responding to the decoherence barrier reveals a fascinating shift in how scientists are approaching the entire problem of interstellar travel. Rather than treating decoherence as an obstacle to simply push through with brute force, a growing number of theorists have begun asking whether the solution lies not in overpowering the noise floor, but in outmaneuvering it through precision rather than power. Throughout 2026, several research groups have published early theoretical work exploring what has come to be called quantum shielding, an idea distinct from traditional electromagnetic or thermal shielding. Traditional shielding tries to block external interference from reaching a system. Quantum shielding, as it is being explored in this context, instead attempts to engineer the local quantum environment itself so that interactions with the surrounding vacuum become less likely to cause decoherence in the first place, even if they cannot be prevented entirely. This might involve carefully structuring the boundary of a warp field so that its interactions with vacuum fluctuations tend to cancel out on average, rather than accumulate into destructive interference. Somewhat analogous to how noise cancelling headphones use a mirrored sound wave to cancel out unwanted ambient noise rather than physically blocking it. This idea borrows conceptually from a well-established technique in quantum computing known as dynamical decoupling, where carefully timed sequences of control pulses are applied to a quantum system in order to average out the effects of environmental noise over time, effectively refreshing the system's coherence faster than the environment can degrade it. Applying a similar philosophy to a macroscopic warp field would require technology far beyond anything currently available, since it would involve manipulating the quantum state of an enormous, curved region of spacetime with a level of precision and speed that dwarfs even our most advanced quantum computing control systems. Nonetheless, the theoretical framework suggests that even if it cannot be eliminated, might potentially be managed or delayed long enough to allow a warp bubble to reach its propagation threshold before collapsing. A second and closely related avenue of research explores whether the answer lies not in brute force energy generation at all, the approach that dominated warp drive research for the first 3 decades following Alcubierre's original paper, but in something more akin to precision frequency phase locking. This concept draws inspiration from fields as varied as laser physics and radio engineering, where achieving a desired effect often depends less on raw power and more on matching frequencies with extraordinary precision, allowing relatively modest inputs to produce outsized effects through resonance and constructive interference. Some theorists have speculated that if the quantum fields responsible for warp bubble stability could somehow be phase-locked to a natural frequency, inherent in the vacuum's own fluctuations, rather than fighting against those fluctuations, the resulting stability might be dramatically improved, reducing the effective decoherence rate without requiring anything close to the energy levels once thought necessary. It is important to be honest about where this research currently stands. These are early theoretical proposals, explored primarily through mathematical modeling and simulation rather than any physical experiment, and enormous uncertainty remains about whether such approaches could ever be implemented at the scale required for an actual warp bubble. Some physicists remain skeptical that any shielding or phase-locking technique, however clever, could ever fully overcome a noise flaw that appears to be woven into the fundamental structure of space-time itself. Others argue that history has repeatedly shown seemingly insurmountable physical barriers yielding to sufficiently creative engineering solutions once the underlying physics is properly understood, pointing to examples ranging from the sound barrier to the once seemingly impossible challenge of maintaining stable nuclear fusion reactions for even brief periods in laboratory conditions. This ongoing debate matters enormously for how we think about humanity's timeline toward becoming a genuinely interstellar civilization, a question that has occupied science fiction writers and serious physicists alike for generations. Before the decoherence barrier became a central focus of theoretical discussion, much of the public conversation around warp drives centered almost entirely on energy. How many stars worth of power would be needed? Whether exotic matter with negative energy density could ever be produced in sufficient quantities? And whether advances in areas like fusion power or matter-antimatter annihilation might eventually close that gap? These questions remain important, but the growing recognition of the decoherence problem suggests that even a civilization with functionally unlimited energy might still find itself unable to build a working warp drive if it has not also solved the far more subtle problem of maintaining quantum coherence across a macroscopic, curved region of spacetime. This reframing has real consequences for how physicists categorize the difficulty of interstellar travel, using frameworks like the famous Kardashev scale, originally proposed by the Soviet astronomer Nikolai Kardashev in 1964 to classify civilizations according to how much energy they can harness, ranging from a Type 1 civilization capable of using all the energy available on its home planet to a Type 2 civilization capable of harnessing the entire energy output of its home star, to a Type 3 civilization capable of harnessing the energy of an entire galaxy. If decoherence truly represents an independent barrier separate from raw energy availability, then simply advancing along the Kardashev scale toward greater and greater energy mastery might not, by itself, guarantee eventual faster-than-light capability. A civilization might reach Type 2 status, commanding stellar levels of energy, and still find itself no closer to solving the coherence problem than we are today, because the two challenges appear to require, fundamentally, different kinds of technological and scientific breakthroughs. Some physicists have begun proposing an entirely new axis for measuring technological advancement, one focused not on energy mastery but on what might be called coherence mastery, the ability to maintain quantum coherent states across increasingly large systems, for increasingly long durations, in increasingly hostile environmental conditions. Under this framework, a civilization's true readiness for interstellar travel might be better measured by how long they can preserve a macroscopic quantum coherent state, whether in a quantum computer, a large-scale quantum communication network, or eventually a warp field, rather than by how many joules of energy they can generate and direct. This remains a speculative reframing rather than an established scientific consensus, but it reflects a genuine and growing shift in how serious researchers are thinking about the problem. There is also a fascinating parallel worth exploring here between the barrier-facing warp drives and the practical challenges facing quantum communication networks here on Earth, an area of research that has advanced considerably in recent years and offers real-world data about how difficult it is to preserve coherence across distance. Quantum key distribution systems, which use the coherence of individual photons to enable theoretically unbreakable encryption, have demonstrated successful coherence preservation across distances of several hundred kilometers using fiber optic cables, and even longer distances using dedicated satellite links that avoid much of the decoherence introduced by scattering and absorption in Earth's atmosphere. These successes are genuinely impressive, but they also come with an important caveat. They involve preserving coherence in single photons, among the simplest possible quantum systems, traveling in a relatively controlled environment. Scaling this success up to a macroscopic warp field, involving an enormously more complex quantum system interacting with the uncontrolled vacuum of interstellar space, represents a difference not just of degree but of an entirely different order of complexity. Decoherence is not the only theoretical barrier that has been proposed to explain why faster-than-light travel might remain forever out of reach, and it is worth briefly considering how it fits alongside other, older ideas in this space. Stephen Hawking, in the mid-1990s, proposed what he called the chronology protection conjecture, suggesting that the laws of physics might conspire to prevent the formation of closed time-like curves, the theoretical loops in spacetime that could allow travel backward in time, and the causality, violating paradoxes that would follow, since certain configurations of faster-than-light travel, including some versions of warp bubbles, could in principle be used to construct such closed time-like curves under specific conditions. Hawking speculated that some undiscovered physical mechanism might prevent them from ever actually forming in practice, protecting the universe from the logical contradictions that time travel paradoxes would introduce. The decoherence barrier we have been exploring throughout this discussion offers an intriguing, though speculative, possible mechanism for exactly this kind of chronology protection, one grounded not in some mysterious cosmic censorship principle invoked purely to avoid paradoxes, but in ordinary, well-understood quantum mechanics. If decoherence reliably destroys the coherent quantum states required for warp bubbles before they can ever reach a propagation threshold, then perhaps we never need to invoke any special new physics to explain why time travel paradoxes do not occur. The universe might simply be too noisy at the quantum level to ever allow the precise conditions required for closed time-like curves to form in the first place. This remains an open and actively debated question rather than a settled conclusion, but it represents one of the more elegant possible connections between two seemingly unrelated areas of theoretical physics. Meanwhile, actual experimental and engineering efforts toward faster-than-light propulsion concepts have a longer and more grounded history than many people realize, stretching back to serious institutional research programs rather than purely academic speculation. In the early 2000s, the physicist Harold White led a research effort at NASA's Johnson Space Center, informally known as EagleWorks, dedicated to exploring advanced propulsion concepts, including refinements to the Alcubierre metric. White's team conducted laboratory experiments attempting to detect minute spacetime distortions using highly sensitive interferometers, the same basic technology later used with extraordinary success by the Liga Gravitational Wave Observatory to detect ripples in spacetime caused by colliding black holes. While the EagleWorks experiments did not produce confirmed evidence of warp field effects, and some of the early results were later attributed to measurement artifacts rather than genuine spacetime distortion, the program represented a serious, funded attempt to move warp drive research from pure theory into experimental territory, and it helped establish infrastructure and expertise that continues to inform later theoretical work, including the refinements that led to the 2024 simulations mentioned earlier. Alongside warp bubbles, researchers have also explored other exotic spacetime geometries that might, in principle, allow faster-than-light travel or shortcuts across vast cosmic distances, most notably traversable wormholes, theoretical tunnels connecting distant regions of spacetime. Wormholes face many of the same fundamental challenges as warp bubbles, including the requirement for exotic matter with negative energy density to keep the wormhole throat open and stable rather than collapsing under its own gravity. And just as with warp bubbles, more recent theoretical work has begun asking whether quantum decoherence might pose an equally serious obstacle to wormhole stability, since maintaining an open wormhole throat likely requires similarly delicate quantum coherent states, vulnerable to the same vacuum fluctuations and Planck scale noise that threaten warp bubbles. This suggests that decoherence may represent not a narrow problem specific to one particular faster-than-light concept, but a more general challenge facing essentially any theoretical approach to exceeding the speed of light through spacetime. Manipulation. One particularly interesting connection involves the Casimir effect, a real, experimentally confirmed phenomenon where two closely spaced, uncharged conducting plates experience a measurable attractive force due to the way they restrict which vacuum fluctuations can exist in the space between them, effectively creating a small region of negative energy density relative to the surrounding vacuum. First predicted by the Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally with increasing precision throughout the latter half of the 20th century. The Casimir effect represents one of the only known, laboratory-verified sources of negative energy density in nature, and it has been proposed as one possible practical route toward generating at least small amounts of the exotic matter that both warp bubbles and wormholes theoretically require. However, the amounts of negative energy achievable through the Casimir effect using currently feasible plate separations remain many orders of magnitude too small to be relevant for anything approaching warp bubble scale requirements. illustrating just how far current experimental capabilities remain from the theoretical requirements. Even setting the decoherence problem aside entirely, given how many interconnected obstacles stand between current physics and any functioning warp drive. From the astronomical energy requirements of the original Alcubierre formulation, to the vanishingly small amounts of negative energy achievable through mechanisms like the Casimir effect, to the newly appreciated challenge of quantum decoherence, threatening to dissolve any such structure before it can function. It is worth asking how these various threads connect into a coherent overall picture of where humanity actually stands on the path toward interstellar travel. The honest answer, according to most physicists working seriously in this space, is that we remain firmly in the early theoretical stages, with genuine open questions at nearly every level of the problem, from the purely mathematical to the deeply experimental. This does not mean the research is without value or that pursuing these questions is somehow misguided. Throughout the history of science, some of the most important breakthroughs have emerged not from directly solving the original grand challenge that motivated a line of research, but from the unexpected discoveries made while investigating it. The intense theoretical work exploring warp bubble energy requirements throughout the 2000s and 2010s led to significant advances in our understanding of exotic spacetime geometries more broadly. Insights that have found applications in areas ranging from black hole physics to cosmology. Similarly, the growing focus on decoherence as a barrier to macroscopic quantum coherence is driving deeper investigation into fundamental questions about how gravity and quantum mechanics interact. One of the most important open problems in all of theoretical physics, sometimes described as the search for a workable theory of quantum gravity. Quantum gravity, the elusive theoretical framework that would successfully unify general relativity's description of gravity as curved spacetime with quantum mechanics' description of matter and energy at the smaller scales, remains one of physics' greatest unsolved puzzles. Despite nearly a century of effort from some of the most brilliant minds in the field, competing approaches, including string theory, loop, quantum gravity, and a range of other, less prominent frameworks, each offer different mathematical pictures of how spacetime might behave at the Planck scale, and each makes somewhat different predictions about the nature and severity of quantum decoherence in curved spacetime environments like the boundary of a hypothetical warp bubble, until experimental evidence can distinguish between these competing frameworks, and until we have direct experimental access to physics at scales anywhere close to the Planck length, which remains far beyond the reach of even our most powerful particle accelerators. The precise mathematical details of how severely decoherence would affect a real warp bubble remain genuinely uncertain, even as the general qualitative picture that decoherence poses a serious obstacle appears increasingly well supported across multiple independent theoretical approaches. This uncertainty cuts in interesting directions when we try to estimate a realistic timeline for humanity's interstellar future. Optimistic voices point out that physics has a long history of transforming seemingly fundamental barriers into merely difficult engineering challenges once the underlying science becomes better understood, citing examples like the sound barrier, once thought to represent an absolute physical limit before Chuck Yeager and his research team demonstrated in 1947 that it was simply a matter of appropriate aircraft design, or the challenge of achieving controlled nuclear fusion, which decades of dedicated research have gradually transformed from seemingly impossible into merely extraordinarily difficult, with several experimental reactors around the world now achieving net energy gained from fusion reactions under carefully controlled laboratory conditions. More cautious voices counter that decoherence appears to be a different category of obstacle entirely, rooted not in engineering limitations that might yield to sufficiently clever technology, but in what may be an intrinsic, unavoidable feature of how quantum mechanics interacts with any sufficiently large, sufficiently complex, coherent system, a feature that shows up consistently across completely different physical contexts. From laboratory quantum computers to black hole event horizons to the theoretical mathematics of warp bubbles themselves. If this more cautious interpretation proves correct, faster-than-light travel through spacetime manipulation might not simply require better engineering, but might require an entirely different theoretical approach that somehow sidesteps the decoherence problem altogether, an approach that no one has yet identified, and which might not exist at all within the framework of physics as we currently understand it. It is worth pausing here to consider why this question matters beyond pure scientific curiosity, because the implications of solving or failing to solve the decoherence problem extend well beyond the specific question of warp drives. Every advance in our understanding of quantum decoherence carries direct benefits for fields far closer to practical application today, most notably quantum computing, where researchers are engaged in an ongoing, high-stakes effort to extend coherence times and scale up the number of qubits that can be reliably controlled simultaneously. Breakthroughs in understanding how environmental noise interacts with quantum systems, whether discovered through warp drive research or through direct quantum computing research, tend to feed back into both fields, since the underlying physics governing decoherence does not particularly care whether the quantum system in question is a qubit inside a refrigerated processor or a theoretical, exotic, space-time geometry. This cross-pollination between fields is not merely incidental. Some of the most promising theoretical techniques being explored for warp bubble stabilization, including the dynamical decoupling-inspired shielding concepts discussed earlier, originated directly from quantum computing research, where scientists first developed these techniques to extend the practical usefulness of early, extremely fragile quantum processors. As quantum computing continues to mature, with coherence times gradually extending and error correction techniques becoming more sophisticated, each incremental improvement offers physicists working on more exotic applications, including warp drive theory, a richer and more refined toolkit for thinking about how coherence might be preserved in increasingly demanding environments. There is also a fascinating parallel worth drawing to the field of quantum error correction more broadly, an area of research dedicated to protecting quantum information from the corrupting effects of decoherence, not by preventing decoherence entirely, an approach that appears fundamentally impossible given our current understanding of quantum mechanics, but by encoding quantum information redundantly across multiple physical qubits in such a way that errors introduced by decoherence can be detected and corrected before they destroy the encoded information. This approach, pioneered in the mid-1990s by researchers including Peter Shaw and Andrew Steen, has become absolutely central to the entire field of practical quantum computing, and some theorists have begun to wonder whether an analogous approach might eventually prove relevant to warp bubble stability. Could a warp bubble, in principle, be constructed using some kind of redundant quantum encoding, distributing the information necessary to maintain its exotic geometry across a structure resilient enough to withstand and correct for a certain amount of decoherence, rather than requiring perfect, uninterrupted coherence throughout its entire formation and propagation? This remains an extremely speculative idea, discussed only in the most preliminary theoretical terms by a small number of researchers, and it faces enormous obstacles, not least the fact that quantum error correction, as currently understood, requires active, continuous intervention by an external control system, capable of measuring and correcting errors without destroying the very coherence it is trying to protect. A delicate balancing act that becomes exponentially more difficult as system size and complexity increase. Nonetheless, the fact that researchers are even beginning to explore such analogies illustrates how deeply the practical lessons of quantum computing are beginning to inform theoretical work on far more exotic and currently unattainable technologies beyond quantum computing. Insights into decoherence also carry implications for our broader understanding of the transition between the quantum and classical worlds, a question that touches on some of the deepest and most philosophically interesting aspects of physics. Why does the everyday world we experience, filled with objects that have definite positions, definite velocities, and definite properties, emerge from an underlying quantum reality where particles can exist in superpositions of multiple states simultaneously? Decoherence theory offers one of the most compelling and widely accepted answers to this question, explaining classicality as an emergent phenomenon arising from the overwhelming complexity of interactions between quantum systems and their environments, rather than requiring any fundamentally new physics separate from quantum mechanics itself. Every experiment that probes the boundary between quantum and classical behavior, whether conducted in a quantum computing laboratory, an optomechanical decoherence experiment, or eventually, perhaps, in a future attempt to stabilize a warp field, contributes to our understanding of this profound and still incompletely resolved question about the fundamental nature of reality. This decoherence barrier also offers an intriguing, if speculative, angle on one of the most enduring puzzles in all of science, the Fermi paradox, the apparent contradiction between the high probability that intelligent life should exist elsewhere in our vast galaxy, given the sheer number of stars and planets available, and the total absence of any confirmed evidence that it does. Among the many proposed explanations for this silence, ranging from the possibility that intelligent life is simply extraordinarily rare, to the possibility that advanced civilizations tend to destroy themselves before achieving interstellar capability, some researchers have floated the idea that faster-than-light travel might simply be impossible for any civilization, regardless of how technologically advanced it becomes, which would naturally explain why we have never observed evidence of interstellar visitors or expansive galactic civilizations, since even a civilization millions of years more advanced than our own would remain confined, like us, to sublight speeds across the vast, empty distances between stars. If the decoherence barrier proves to be a truly fundamental limitation, woven into the basic structure of quantum mechanics and spacetime rather than merely an engineering challenge waiting for a sufficiently advanced technological solution, it would lend meaningful support to this particular explanation for the Fermi paradox. Every civilization, no matter how sophisticated its energy generation or how deep its understanding of exotic matter, would still face the same fundamental noise floor imposed by the vacuum's quantum fluctuations, the same exponential scaling of decoherence rates with system size and complexity, and the same requirement for essentially perfect coherence across the entire structure of any warp field long enough for it to reach a usable propagation threshold. Under this scenario, the galaxy might be full of intelligent civilizations, all separately arriving at the same sobering conclusion that the stars, while visible and reachable in principle over sufficiently long timescales, using conventional sublight propulsion, remain forever out of reach for anything resembling the faster-than-light travel imagined in science fiction. It is worth emphasizing, however, that this remains one hypothesis among many competing explanations for the Fermi paradox, and it should not be treated as a confirmed conclusion. The decoherence barrier, as serious and well-grounded as the underlying physics appears to be, still represents an area of active theoretical research rather than a definitively proven, insurmountable law of nature. It remains entirely possible that future breakthroughs in quantum gravity, in our understanding of vacuum fluctuations, or in entirely unforeseen areas of physics, could reveal pathways around the coherence problem that current theory simply has not yet identified. Science has a long history of barriers that seemed absolute until they were not. An intellectual humility requires acknowledging that possibility even while taking the current evidence seriously. Looking toward the near future, researchers hoping to make genuine experimental progress on this question face significant practical challenges, since testing decoherence effects relevant to warp bubble physics would require generating and measuring extremely subtle space-time curvature effects, well beyond what current laboratory technology can achieve. Some proposals under discussion involve extending the kind of ultra-sensitive interferometry pioneered by projects like LIGO, potentially combined with cryogenically cooled, carefully isolated test masses placed into quantum superposition states to search for any measurable signature of gravitationally induced decoherence, building directly on the theoretical predictions made by Penrose and Diacy discussed earlier. If successful, such experiments would not directly demonstrate anything close to a functioning warp bubble, but they would provide crucial experimental data about how gravity and quantum coherence interact at scales currently accessible to laboratory technology, data that would help refine and constrain the theoretical models physicists use to predict decoherence rates in far more extreme, currently unattainable scenarios like an actual warp field. Other proposals look towards space itself as a potential laboratory, taking advantage of the extended periods of microgravity and reduced environmental interference available aboard orbiting platforms to conduct quantum coherence experiments that would be extraordinarily difficult to perform under the vibration and gravitational noise present on Earth's surface, building on the successful precedent set by earlier satellite-based quantum experiments, including quantum key distribution demonstrations conducted using dedicated satellites capable of maintaining photon entanglement across distances far greater than achievable through ground-based fiber optic networks. Future missions, specifically designed to probe the limits of macroscopic quantum coherence in the space environment, could offer valuable insights into whether the vacuum's noise floor behaves differently, or perhaps more favorably, outside the complicating influence of Earth's atmosphere and gravitational environment. Government and institutional funding for this kind of fundamental propulsion research has waxed and waned considerably over the decades, reflecting both the speculative nature of the work and its potential long-term significance. The Defense Advanced Research Projects Agency, commonly known as DARPA, funded a program called the 100-Year Starship Initiative beginning around 2011, explicitly designed to seed long-term thinking about interstellar travel across multiple generations of researchers, recognizing that problems as fundamental as the decoherence barrier are unlikely to be solved within any single funding cycle or even within a single human lifetime. Similarly, organizations, including the Breakthrough Initiatives, founded in part with private funding from the physicist and entrepreneur Yuri Milner, have supported theoretical and observational work relevant to interstellar travel and the broader search for extraterrestrial intelligence, including funding conferences and research grants exploring exactly the kind of exotic propulsion physics we have been discussing throughout this documentary. This pattern of funding reflects a broader truth about how genuinely difficult scientific problems tend to be solved, not through a single dramatic breakthrough, but through decades, and sometimes centuries, of incremental progress across multiple, seemingly unrelated fields that eventually converge on a shared solution. The eventual development of nuclear fusion power, still ongoing today despite research efforts stretching back to the 1950s, offers a sobering example of just how long even well-funded, clearly defined scientific challenges can take to resolve. And the decoherence barrier facing warp drives appears, if anything, considerably more fundamental and less well-defined than the challenge of achieving controlled fusion, suggesting that any eventual solution, if one exists at all, likely remains generations away at the very least. There is also a deeper, more philosophical dimension to this entire line of inquiry that extends beyond the purely technical physics, one that touches on how humanity understands its own place within the universe and the ultimate limits of what our species might eventually achieve. For much of the 20th century, science fiction cultivated an expectation, deeply embedded in popular culture, that faster-than-light travel represented an inevitable, if distant, technological milestone, a natural extension of humanity's historical pattern of eventually overcoming seemingly impossible physical barriers through sufficient ingenuity and persistence. The growing recognition of the decoherence barrier represents a meaningful challenge to that comfortable assumption, suggesting that some physical limits might genuinely be more fundamental than mere engineering challenges, rooted not in the current state of our technology but in the deep mathematical structure of quantum mechanics and spacetime itself. This does not necessarily represent bad news, despite how it might initially feel to anyone who grew up hoping to witness humanity's first faster-than-light voyage, confronting genuine physical limits, rather than assuming all barriers are simply engineering problems waiting to be solved with enough time and resources, is itself a form of scientific maturity, one that redirects research energy and resources toward avenues that might prove more fruitful. If faster-than-light travel through space-time manipulation genuinely proves impossible, or so overwhelmingly difficult as to be effectively impossible for any foreseeable future civilization, this understanding could redirect attention and resources toward alternative approaches to interstellar travel, including generation ships, suspended animation technologies, or entirely novel concepts not yet conceived, approaches that work within the light speed limit rather than attempting to circumvent it, potentially accelerating progress in those more tractable directions precisely because researchers stop chasing a goal that the underlying physics may simply not permit. There is a certain irony worth sitting with here, one that captures something essential about how science actually progresses in the real world, as opposed to how it is often portrayed in popular imagination. The public conversation around faster-than-light travel has, for decades, fixated overwhelmingly on energy, treating it as the single defining obstacle standing between humanity and the stars, largely because energy requirements are relatively easy to calculate, easy to express in dramatic, headline-friendly numbers, and easy to visualize as a straightforward engineering challenge, however extreme, requiring simply more power, more exotic fuel, or more advanced reactors. Decoherence, by contrast, resists this kind of simple, intuitive framing. It cannot be reduced to a single large number representing joules or watts. It emerges instead from the accumulated, probabilistic effects of countless microscopic quantum interactions, a phenomenon that is genuinely difficult to visualize, difficult to calculate precisely without extremely sophisticated mathematics, and correspondingly difficult to communicate to a general audience, which likely explains why it received comparatively little popular attention for so long, even as it was quietly emerging as perhaps the more fundamental of the two obstacles among physicists actually working closely with the underlying mathematics. This pattern, where the most fundamental scientific obstacles are often the least dramatic and the least intuitive, repeats throughout the history of physics in ways that are worth appreciating. When physicists first began seriously considering nuclear fusion as a potential energy source in the mid-20th century, the popular imagination focused heavily on the raw power of fusion reactions, the same process that powers the sun and the hydrogen bomb, while the far more subtle and ultimately more challenging problem of achieving stable, controlled plasma confinement, keeping a ionized gas contained long enough for sustained fusion reactions to occur without touching and destroying the walls of any physical container, took decades longer to be widely appreciated as the true central challenge of fusion research. A challenge that continues to occupy researchers even today. More than 70 years after fusion power was first seriously proposed as an achievable energy source, decoherence appears to be following a remarkably similar trajectory within warp drive research, initially overshadowed by the more dramatic, more easily quantified challenge of exotic energy requirements, only to emerge as theoretical understanding deepens, as potentially the more fundamental and more difficult obstacle to actually overcome. This pattern offers a valuable lesson about the nature of scientific progress more broadly, that the most visible, most easily quantified challenges are not always the ones that ultimately determine whether a given technological dream becomes achievable, and that genuine scientific maturity often requires looking past the dramatic headline numbers to identify the quieter, more subtle obstacles that may prove decisive in the end. It is also worth examining more carefully what the 2026 quantum shielding research actually involves at a technical level, since the term itself can easily be misunderstood as implying something closer to science fiction force fields than the genuine, if speculative, physics being explored. The research groups working in this space are not proposing anything resembling a protective barrier that simply blocks vacuum fluctuations from reaching a warp field, an idea that would likely violate basic principles of quantum field theory, since vacuum fluctuations are not localized disturbances that can be screened out the way electromagnetic radiation can be blocked by a Faraday cage. Instead, the proposals under discussion involve far subtler concepts, drawing on ideas from a branch of physics called open quantum systems theory, which studies how quantum systems that cannot be perfectly isolated from their environment nonetheless retain useful coherent properties for longer than naive calculations might initially suggest, provided the coupling between system and environment is structured in particular, mathematically favorable ways. One specific concept explored within this framework involves what physicists call decoherence-free subspaces, special configurations of a quantum system where certain combinations of states happen to be immune, or at least significantly more resistant to particular types of environmental noise, even though the system as a whole remains coupled to its environment in the ordinary sense. This is not merely a theoretical curiosity. Decoherence-free subspaces have been experimentally demonstrated in laboratory quantum computing systems, where researchers have shown that carefully chosen combinations of qubit states can maintain coherence significantly longer than individual qubits, considered in isolation, because the particular symmetry of the chosen subspace happens to be insensitive to the dominant noise sources affecting the system. Applying this concept to a hypothetical warp bubble would require identifying whether some analogous symmetry exists within the quantum field configurations responsible for the bubble's exotic geometry, a mathematically demanding question that current researchers have only begun to explore in the most preliminary terms. The challenge, as several theorists working in this area have acknowledged, is that decoherence-free subspaces identified in laboratory quantum computing contexts typically exploit very specific, well-characterized noise sources, such as particular types of electromagnetic interference or specific vibrational modes within a physical apparatus. The noise floor relevant to warp bubble decoherence, arising from Planck scale, vacuum fluctuations, and potentially from gravitationally induced decoherence effects along the lines proposed by Penrose and Dios, remains far less well characterized, making it correspondingly difficult to identify what kind of decoherence-free subspace, if any, might offer meaningful protection. This is precisely the kind of foundational uncertainty that continued experimental work in quantum, gravity, and gravitationally induced decoherence testing, discussed earlier, would help resolve, illustrating once again how progress on this seemingly narrow propulsion question depends heavily on answering much broader, more fundamental questions about the relationship between gravity and quantum mechanics beyond the technical proposals for shielding and phase locking. Some researchers have begun exploring an entirely different philosophical approach to the decoherence problem, one that questions whether the traditional warp bubble concept, requiring a single, continuous, perfectly coherent quantum state spanning the entire structure, represents the only viable path forward, or whether alternative geometric configurations might sidestep the coherence requirement altogether. One line of speculative theoretical work has examined whether a series of many small, rapidly refreshed micro-warp fields, each individually much easier to maintain in a coherent state due to their smaller size and correspondingly slower decoherence rate, might be chained together in rapid succession to achieve a similar net propulsion effect to a single large warp bubble, without ever requiring any individual component of the system to maintain coherence for longer than its naturally short, but manageable, decoherence timescale allows. This approach draws a loose conceptual parallel to how classical computer processors achieve enormously complex calculations not through any single monolithic operation, but through the extraordinarily rapid execution of vast numbers of comparatively simple individual operations, each easy to perform reliably on its own. Whether an analogous strategy could work for warp field generation remains deeply uncertain and highly speculative, since it would require solving extraordinarily difficult synchronization problems, ensuring that each successive micro-warp field forms, propagates, and dissolves in precise coordination with its neighbors, all while maintaining the smooth, continuous space-time geometry needed to actually transport a physical object without subjecting it to potentially destructive tidal forces or discontinuities at the boundaries between successive fields. Nonetheless, the fact that researchers are exploring such creative reconceptualizations of the basic warp bubble geometry demonstrates the kind of genuine scientific ingenuity being brought to bear on this problem, even in the absence of any clear indication that a workable solution exists. Skeptics within the physics community, and there are many, argue that these various proposals, from quantum shielding to decoherence-free subspaces to chained micro-warp fields, share a common weakness. They each attempt to solve a fundamentally quantum mechanical problem using techniques and intuitions developed for comparatively simple laboratory systems involving relatively small numbers of particles, without fully grappling with the sheer scale difference involved in warping a macroscopic region of spacetime, large enough to transport an actual spacecraft. The number of interacting degrees of freedom involved in even a small-scale warp bubble would likely dwarf anything achieved in current quantum computing or quantum optics experiments by many orders of magnitude, and it remains entirely possible that techniques which work well for systems involving dozens or even thousands of particles simply fail to scale in any useful way when applied to systems involving the astronomical numbers of interacting quantum degrees of freedom that a macroscopic warp field would require. This scaling objection touches on something physicists call the quantum to classical transition, a gradual, well-documented phenomenon where systems composed of increasingly large numbers of particles behave increasingly classically, losing their capacity for quantum behaviors like superposition and coherent interference, not through any single sharp boundary but through a smooth, continuous crossover that depends on the specific details of how the system interacts with its environment. Understanding precisely where this crossover occurs for any given physical system, and how it might be pushed toward larger scales through clever engineering, remains one of the most actively researched questions in quantum foundations, the subfield of physics dedicated to understanding the deepest conceptual underpinnings of quantum mechanics itself. Every experimental success in maintaining coherence for larger, more massive, or more complex systems, from the molecular interference experiments mentioned earlier to increasingly ambitious quantum computing architectures involving growing numbers of interconnected qubits, pushes this crossover boundary a little further, offering incremental, hard-won evidence about just how far the quantum world can be extended before classical behavior inevitably takes over. Whether this boundary can ever be pushed far enough to accommodate something on the scale of a warp bubble remains, honestly, one of the most genuinely open questions in this entire area of physics, and reasonable, well-informed scientists currently disagree about the answer. Some point to the exponential difficulty of maintaining coherence as system size grows and conclude that macroscopic warp bubbles likely remain permanently out of reach, a fundamental rather than merely practical limitation. Others point to the historical pattern of quantum coherence being successfully extended to increasingly large and complex systems over the past several decades, from single photons to large molecules to engineered mechanical resonators containing trillions of atoms, and argue that continued progress, driven by advances in materials, science, control, engineering, and our theoretical understanding of decoherence itself, might eventually extend coherence to scales currently considered unimaginable, much as earlier generations of physicists once considered maintaining coherence in even a handful of interacting particles to be hopelessly impractical. What makes this scientific moment particularly interesting is that we appear to be witnessing, in close to real time, a genuine paradigm shift in how the physics community frames the entire challenge of faster-than-light travel. For the better part of a century, the conversation was dominated almost entirely by general relativity, by Einstein's equations, and by the search for exotic solutions to those equations that might permit apparent faster-than-light effects without technically violating relativity's local speed limit. Quantum mechanics, when it entered the conversation at all, typically appeared only in discussions of where the exotic negative energy matter required for such solutions might actually come from. The growing recognition that quantum decoherence represents an independent, and possibly more fundamental, obstacle marks a meaningful shift toward treating faster-than-light travel as fundamentally a quantum mechanical problem as much as a general relativistic one, requiring genuine synthesis between two branches of physics that have historically been notoriously difficult to reconcile. This synthesis is, of course, precisely what a successful theory of quantum gravity would need to provide, which brings the conversation full circle back to one of the deepest, most stubbornly unresolved questions in all of theoretical physics. It is a fitting, if somewhat humbling, conclusion to recognize that the practical question of whether humanity might ever build a working warp drive turns out to be inseparably entangled with the far more abstract, far more fundamental question of how gravity and quantum mechanics fit together at the most basic level of physical reality. Solving one problem may well require solving the other, and given that physicists have been working on unifying gravity and quantum mechanics for the better part of a century without a definitive resolution, This connection alone suggests that any confident timeline for faster-than-light travel remains, at best, an exercise in informed speculation rather than genuine prediction. None of this uncertainty should be mistaken for pessimism about the value of continuing this research. Each new theoretical proposal, whether it ultimately proves successful or not, deepens our collective understanding of quantum mechanics, general relativity, and the increasingly important space where the two theories meet and, so far, imperfectly overlap. Each new experimental technique developed to test decoherence at ever larger scales, whether in a laboratory interferometer, chasing gravitationally induced collapse, or a satellite testing quantum coherence in the space environment, extends the boundary of what human technology can measure and manipulate at the quantum level. Boundaries that carry direct practical benefits for fields as immediately relevant as computing, secure communication, and precision measurement, regardless of whether warp drives ever move beyond theoretical speculation. So where does this leave us? Standing at the edge of what current physics can confidently tell us about faster-than-light travel. We know, with a very high degree of confidence, that the vacuum of space is not empty, that it churns constantly with quantum fluctuations reaching down to the smallest conceivable scales, and that any coherent quantum structure attempting to exist within that environment faces a genuine, well-documented tendency to lose its coherence through entanglement with its. We know that this decoherence problem scales unfavorably as systems grow larger and more complex, a pattern confirmed repeatedly in laboratory quantum computing research, even as scientists work tirelessly to push the boundaries of what remains achievable. And we know that any warp bubble, according to the best mathematical models currently available, would require exactly the kind of large-scale, sustained quantum coherence that this noise floor appears designed, in the deepest sense of physical law rather than intention, to prevent. What we do not know is whether this barrier represents a truly fundamental, insurmountable limit woven permanently into the structure of physical law, or whether it represents merely the current frontier of human understanding, destined to yield eventually to insights we cannot yet anticipate, much as earlier generations of physicists once considered problems like controlled nuclear fusion or macroscopic quantum coherence in massive molecules to be permanently beyond reach, only to watch those boundaries gradually shift under the pressure of sustained, patient scientific effort. We do not yet know whether gravity itself actively contributes to decoherence, as Penrose and Diossi have proposed, an idea that remains experimentally untested but increasingly within reach of near-future laboratory technology. We do not know whether quantum shielding, phase locking, decoherence-free subspaces, or some other approach not yet conceived might offer a genuine pathway around the noise floor, or whether all such efforts are ultimately doomed by the sheer scale difference between laboratory quantum systems and anything resembling a macroscopic warp field. Current research continues to advance on multiple fronts simultaneously, each contributing a small piece to this much larger puzzle. Quantum computing researchers continue extending coherence times and scaling up the size of reliably controllable quantum systems, incrementally testing the practical limits of the quantum to classical transition. Experimentalists continue refining ultra-sensitive interferometry techniques, inching closer to the sensitivity required to test gravitationally induced decoherence directly in laboratory conditions. Theorists continue exploring the mathematical relationship between general relativity and quantum field theory, searching for the elusive framework of quantum gravity that might finally explain, with genuine precision rather than educated speculation, exactly how severely and under what specific conditions a macroscopic warp field would actually and mission planners and propulsion researchers Informed by all of this deepening theoretical understanding, continue reassessing what a realistic, evidence-based timeline toward interstellar capability might actually look like, a timeline that, if the decoherence barrier proves as fundamental as current evidence increasingly suggests, may well extend far beyond anything imagined by earlier generations of science fiction writers and space enthusiasts. This question remains scientifically important, not because we expect a definitive answer next year, or even within our lifetimes, but because it sits at the genuine, unresolved frontier where our two most successful physical theories, general relativity and quantum mechanics, still fail to speak the same language. A gap in human understanding that ranks among the most significant unsolved problems in all of science. Every insight gained while probing this gap, whether through the lens of warp drive physics or through more directly applicable research into quantum computing and quantum gravity, brings humanity a little closer to a complete and unified picture of how the universe actually works at its most fundamental level. Perhaps that unified picture will eventually reveal a pathway to the stars that current physics cannot yet see. Or perhaps it will confirm, with mathematical rigor rather than mere speculation, that the quiet, restless noise of the quantum vacuum truly is one of the universe's most stubborn and permanent laws, a boundary as real and as unyielding as the speed of light itself. Either way, the search for that answer continues, carried forward by researchers willing to sit patiently with genuine uncertainty, following the evidence wherever it ultimately leads, in pursuit of an understanding that may, in the end, matter far more than the warp drive that first inspired the question. It is worth remembering, too, that the history of physics is filled with moments where the missing piece of a puzzle turned out to be hiding in plain sight, overlooked not because it was too obscure to notice, but because researchers were looking in the wrong direction, focused on the loudest, most obvious obstacle while a quieter, more fundamental one waited patiently underneath. The energy requirements of a warp bubble were always going to be dramatic, always going to make for compelling headlines and vivid mental images of stars worth of power funneled into a single spacecraft. Decoherence offered no such spectacle. It crept in through the mathematics of open quantum systems, through the patient, unglamorous work of physicists studying qubits in refrigerated laboratories, through decades of careful theoretical refinement that rarely made headlines of its own. And yet it may turn out to be the truer gatekeeper standing between humanity and the stars. A reminder that the universe rarely reveals its deepest secrets through drama alone, but often through the quiet, persistent noise that was there all along, waiting for someone patient enough to listen. There is one more thread worth pulling on before we close, because it speaks directly to how ordinary people, not just physicists working at the frontier, can meaningfully engage with a question this abstract. The mathematics of decoherence, exotic space-time curvature, and quantum gravity is undeniably dense, accessible in its full technical detail only to specialists who have spent years mastering the relevant formalism. But the underlying intuition that the universe resists large-scale quantum coherence the way a turbulent sea resists a perfectly still reflection is something anyone can grasp, and that accessibility matters. Public understanding of frontier physics has historically shaped which questions receive sustained funding, which young researchers choose to dedicate their careers to a given problem, and which long-shot ideas survive long enough in the public imagination to eventually attract the patient. Decades-long institutional support that genuinely difficult problems require. The story of the decoherence barrier, in other words, is not just a story about warp bubbles and vacuum fluctuations. It is also a story about how a civilization decides which impossible-sounding questions are worth taking seriously. And it is a question every curious mind is invited to keep asking.